right. Well, hello everyone. We're gonna go ahead and start on some practice problems for Chapter 11. Okay, this had to do with electrochemistry, so we can get a little bit more familiar with using this table of reduction potential. So the first thing I want to do is kind of sort some things out on this table for you. Okay, so that you can use this easily. You can either use the table the way I show you, or we can use the horizontal line method, or we can use it in conjunction. It doesn't matter. I would say use them both while you're practicing this and preparing for your exam so that you can see which one you're the most comfortable with. Okay, so here we go. All right, so one of the things we need to remember is that when we're looking at these reduction potentials, okay, that the more positive the reduction potential that we see here, right, that means the more stronger the reducing agent. Okay, so how does this work? All right, so the thing you need to think about is that as I increase on the left side, okay, everything on the left side of the arrow, all right, this is an increase in the strength of the oxidizing agent, right? So we're increase in strength. Oh, sorry, you can't see me. Of the oxidizing agent. Okay, and that means that everything on the right side of the arrow, okay, so we have, you know, the 2F minus, 2H2O, right, everything on this side, okay, so we'll just kind of draw an arrow coming down this way. Everything on this side, this is an increase in strength and reduction potential, okay, increase in strength of the reduction agent, sorry, of the reducing agent, okay. Okay, so this is just an increase in strength of reducing agent, and the same thing goes over here, okay. It's just we didn't want to put the whole table coming down. All right, so that's just some things that we need to do. We need to think about. Another thing we need to think about is that when we're dealing with a spontaneous reaction, all right, so I'm going to kind of do a thing here. That was awful. Anyway, it's spontaneous, okay? This is for a spontaneous reaction. All right, so what we have to remember is that the cathode's on top, and it's in a forward direction, and the anode is on bottom in a reverse direction, okay? And we need to remember that the cell potential for a spontaneous reaction, okay, so the cell potential for spontaneous reaction has to be a positive value, okay? It must be a positive potential. All right, and if we have a non-spontaneous, okay, then we're going to have the opposite, right, where we're going to have anode here and cathode on the bottom. All right, and so this is if we're dealing with electrolytic cells, right, where we have a battery involved. But the spontaneous, so kind of want to remember that, right? And remember this going down, right? Going down this way on this side. This is an increase in what? In the strength of which one? Oxidizing or reduction? It's the reduction agent, right? Okay. And then going up this way, on the left side, this guy is an increase in oxidizing. Okay, so it follows the same format. Okay, so we need to keep these things in mind. All right, but now let's go ahead and we got in oxidation, being able to determine the oxidation number of each element within a compound is really, really important. If you can't do that, you're going to be in trouble. Okay. So let's look at this. We have K. See, I'm going to just kind of write them apart a little bit. Okay, KClO3. All right. So I'm going to go through this kind of slow, but you really need to be able to do this in your head. And it's asking you, what is the oxidation number of chlorine? So this is the guy that we want to know. Now we know that oxygen has a -2. That's an oxide, right? So we're going to put this guy down as -2. Okay, and then we know that potassium is a +1, all right? So then what we can say is we have 1 plus, we don't know what this is, right? This is x, right? Plus, what do we have? We have 3 minus 2, okay, is equal to 0, because we need the sum of all these charges to equal 0 for the overall charge, to give us a neutral charge, okay? So if this is 1 plus, we don't know, trying to figure that out. What is this guy? It's going to be negative 6, right? Change that to negative 6, okay? And so that's equal to 0. So what does that make x? It means x is equal to plus 5, right? Because if this is negative 6 plus 1, that's going to give us a negative 5. And I need something to offset that negative 5. So that's going to be a plus 5. Okay, so this is my D is my answer, is plus 5. The oxidation state of nitrogen given for all of the following species is correct except for 1. Okay, so in this one we kind of got to go through some things, right? So let's look at it. So we have N2H4. And what do we have here? We have a, if we look at this one is a plus 1. Nitrogen is going to be a what? So this is really plus 4. And I've got 2 of these, so the nitrogen has to be a negative 2. Okay, so when I look here, this N2 is a negative, this nitrogen is negative 2. That's what we say here. So this guy is correct. Okay, let's do a different color for this one so we don't get them confused. There's NH2OH. Okay, so when I do this, I've got a plus 1, a minus 2, and a plus 1, right? And I don't know what oxygen is. So when I look at this, I say, okay, I've got X plus, what is this? Plus 1, right? And then what do I have? I've got a 2, this guy here. Oh, wait a minute, why did I do that? I'm sorry. Yeah, that's N plus 1, but it's times 2. So what I want to do, let me write this a little bit bigger. I'm just going to write down here. I've got this X, but I've got 2 of these hydrogens, right? So I'm going to do 2 times plus 1, because I'm just keeping up with the charges, right? And then I come over here and I've got this oxygen, which I know is a minus 2, but I've only got 1. So I'm going to say, okay, minus 2, and then I've only got 1 hydrogen, so I can say plus 1, and all that is equal to 0, okay? So what I have X plus 2 minus 2 plus 1. So what does that give us? That's equal to 0. So this means that X is equal to negative 1. Right? When we work all that out, you should be able to figure that out. When you do 2 minus 2, that's 0 plus 1. So I need a negative 1 to offset that to give me a 0. So it's negative 1. Oh, so look at this guy. This should be negative 1, and it's not. Okay? So we really don't have to go any further because there's not multiple answers. All right? So this is our answer. But that's okay. I just want to make sure you can do this. So we've got N2O, right? So if this is minus 2, and I've got 2 of these nitrogens, what must the charge on the oxidation state be? It's got to be plus 1, right? Because that gives me a plus 2 minus 2 is 0. And that's what we see here, and that's a check. N2, right, it's equal to 0, right? That's in its elemental form, okay? And now we have HNO2. Okay, so this is minus 2. This is plus 1. So technically, if I do minus 2 times 2, that's minus 4. Plus 1 is going to be what? That's going to be minus 3. So that means this has to be a plus 3. Okay, and that's what I see here. All right, so make sure that you can find oxidation states. All right, so now we have what is the substance in the reaction below? I'm sorry, which substance in the reaction below is the oxidizing agent? So what do we do here? We say, well, let's see. I've got this. We're going to take this Fe2 plus over here to the Fe3 plus. And what's happening? I've got a plus 2 going to a plus 3. And is that a gain or loss in electrons? It's a decrease, right? I'm sorry, it's a decrease in electrons, right? We're losing electrons here. All right. And so if we're losing electrons, right, loss of electrons is what? Oxidation. So this is being oxidized. Okay. And then so now we've got MnO4, okay, and it's going over here to Mn2. Right, so what do we have to do here? Well, you should be able to look at this and find the oxidation state of this, right? So this is going to be, oxygen is -2, right? And so that makes this a -8, okay? And then we have this, so what is that going to do to give us an overall charge of -1? Well, I'm going to need a +7, right? I'm going to need a +7. Let me just write this over here. If I have MnO4 minus, that means that I have X plus, this is what, 4 times -2, that's the, we know oxygen is -2, which has an overall charge. This is not an overall neutral molecule, right? This is a -1, it's an ion. So it's a -1, right? So I have X plus -8, right, is equal to -1. And so see, if this is why you can see that we need this to be a +7, right? So 7 minus 8 is going to be what? -1. So this has to be a +7. So we're going from a +7 oxidation state to a +2. This is a gain in electrons, right? So we have reduction. All right. So what does that mean? Which substance in the reaction below is oxidized? Well, which one is oxidized? I'm sorry, which one is the oxidizing agent? Well, if this one is being reduced, then it's the oxidizing agent. And if this one's being oxidized, this is a reducing agent. So MnO4 is going to be our oxidizing agent. Okay. In the equation, in this equation right here, we've got we need to know which one the oxidizing. It's asking, we've got this long equation, we want to know the oxidizing agent, right? Okay. Well, we just did this MnO4. Now this is a +1. So what do we have here? Now this time, it's not an overall charge of -1. Here we've got this potassium ion to offset that. So what do I have? I've got a, a -2, so that's -8, right? +1, right, is going to give me a -7. So this guy has to be a +7 to offset, right? And so if I do this, and I'm going to go, well, I'm not going to do that. I'm going to go over here to the other one. And what is this one? Well, if I look at SO4, 2 minus, remember our polyatomic anions, then I know that this guy has to be a +2. Okay, so what's happening here? I've got a loss in electrons, right? And if I'm sorry, I've got a gain of electrons. I've got a gain. So we're going from a +2 to a -2. So we have an increase in electrons. And if we have an increase in electrons, what's going on? We have reduction. And if I have reduction right here, then this is my oxidizing agent. Okay, if this one's being reduced, then it's my oxidizing agent. So KMnO4 is my oxidizing agent. Okay, now we got lucky on that one, and it just worked out. Okay. All right. Now let's go to this one. All right, we want to write the balanced redox reaction. Let me see if I have another one of those tables. It doesn't have stuff on it. I shouldn't have printed these double-sided like this so you could see the tables. Okay, so, well, let's see. Write the balanced redox reaction consisting of the following half reactions. Okay. Well, first thing we want to do is we need to equalize our reactions, our electrons. Another thing we want to do is take a look at this to determine which one is the reducing agent and which one is the oxidizing agent. So let's do this. Okay, so we got this guy. Now, I'm sorry, I got lost in thought with something. Okay, so I have 5 electrons here, and I've got 4 electrons here. So I'm going to have to cross multiply, right? And do 4 here and 5 here. And that's going to give me, let's just write this out. I'm going to have 4, and we'll take this MnO4 minus, right? And then plus, now when I look at my hydrogens, when I multiply this through, how many hydrogens am I going to have here? I'm going to have 20, right? And how many hydrogens am I going to have here? 32. All right, and so 20 from 32 is going to, I can cancel some of these out, right? So that I'm going to have 12 hydrogens, H pluses left over, okay? All right, and that's going to form, because these guys have canceled, right? Now, I'm going to form, what is it, 4, where are we? Mn, 2 plus right here, right? And then that's plus, how many waters are we going to have here? Let's see, we had 10 waters here when I multiplied this through. And here I've got 16 waters, okay? So that's going to leave me with 6 waters on this side, right? And then we're going to have, how many O2s are we going to have? Just 5, right? So 5 O2. So we just cross multiplied everything, and that gave us the reaction, okay? And so if you have, let's look at this next one. If we have solid copper, and we say that it's going to spontaneously reduce, okay? Which of the following is it going to be able to spontaneously reduce? And this is where we're going to go back to our table. I've got to pause you for just one quick second. All right, guys. So I think what I want to do, I'm sorry, I had to leave real quick to go take care of something. But I went through this one problem kind of quick, and with the assumption that you understand it, but the whole point of doing the practice problems is you may not understand it and need more practice. So let me go through this in a little bit more detail. So, all right, because I kind of skipped some steps with you. So the first thing is we've got this MnO4 minus, right, plus 8 H plus 5 electrons to form Mn2 plus H2O, okay? And then we've got this other half reaction of H2O, 2H2O, going to O2 plus 4 H plus 4 electrons, okay? So there's some things we need to look at, because remember what I told you before is if we have a spontaneous reaction, right, then we have cathode is here, anode is going this direction, and cathode's always on top. So that's what we're assuming that we have, right? And if I look at the oxidation of this MnO4, I know that this is a minus 2. So to determine what this is, so a minus 2 times 4 is a negative 8, right? This has a an overall charge of negative 1. So what do I need to add to this negative 8 to get a negative 1? I need a plus 7, right? So this guy is a plus 7. Okay, and it goes over here, and now we're going from a plus 7 to a plus 2. So what's happening? We're having a gain in electrons, right? And so if I have a gain in electrons, then I have reduction going on. Okay, and so this is my redox, or my reduction, I should say, on this side, right? On the top, which is my cathode, and then oxidation happens at the anode, right? And so this is my oxidation here. All right, and so when I look at these, what is the first thing we have to do? We have to equalize the electrons, right? So I've got 5 electrons here, and I've got 4 here. I'm sorry, 4 here. And so what does that mean? That we have to, the least common multiple of this is 20, right? So I'll cross multiply and multiply this one times 4 and this one times 5, right? And I'm going to just go ahead and write that out. So that'll give me 4 MnO4 minus plus, what's 4 times 8 is 32 hydrogens plus 20 electrons. It's going to give me 4 Mn2 plus 4 waters, right? Oh, wait a minute. What was this? This was 4. And so that means this was 16. Sorry, 16 waters. Okay. And now if I do this guy, I've got 10 waters. Now whatever's on the reactant side here stays on the reactant side as we move down. Now right now I'm just multiplying this out and then I'm going to sum them up. But reactants stay on reactants and products stay on products, right? So now I'm going to do this one. So here I've got 10 waters, right, that are going to form 5O2 plus 20 H plus 20 electrons, okay? And so, because we have to equalize the electrons, right? And then we can reduce where we can. So I've got 20 electrons, right? And then if I have 10 waters here, 16 minus 10, this will go in here. That'll leave me with 6 waters, right? And if I look at these hydrogens, I have 20 hydrogens here and 32 here. That leaves me with 12, right? When we cancel out. Okay. And so then I want to write out my balanced equation, right? I'm going to use a different colored pen because I like to underline, you know, whatever it is that I've done. So I'm going to start with my reactants, with my redox, right? So I've got 4 MnO4 minus, okay, then I have plus 12 H plus. I don't do this because they've canceled out. I come down here, my waters are gone, right? So now I can say to form, right, what are my products up here? I've got 4 Mn2 plus 6 waters, and then what do I have left here? I've got 5O2. I should have been underlining these and I wasn't as I went through. Okay, and so that's how you would go through that in a slower way. Okay, but if you were really going to write it all out, this is what you do. Okay. All right. Now let's go on to this next one. All right. So with this guy, it says solid copper will spontaneously reduce which of the following. Okay. Well, you can take this approach one of two ways. You can look at copper and you can write out the redox using that horizontal line method we did for each of this, or we can just look at the table. Okay, so let's first of all circle some things. Okay, and then I'm going to tell you for this exam, you're probably going to want to bring different colored pencils, because or pens or whatever, matte pencils, highlighters, pens, it doesn't matter, because for this to keep up with what you use on the table, okay, because as you circle things or whatever, so you're keeping up with what you're doing. All right, so it says solid copper will spontaneously reduce which of the following. All right, so first of all, we need to know where is solid copper. So if I look here, right, I've got, I think I'm going to, yeah, I'll do this guy. I've got copper, right? Here it is. Okay. Now, here's my copper, and I want to know which of these will spontaneously, copper will spontaneously reduce which of the following. Okay, so here's what are we dealing with? We've got Fe2 plus, so let's look for Fe2 plus. Okay, now we're talking about reducing something, so that means that, you know, we can circle this guy, but this is not the Fe2 plus that we're looking for, and we'll see that in a minute. Let's see, we've got another Fe2 plus over here, okay, and then we've got, what does it say, silver plus, so where's Ag plus? Here's that guy, okay, and then we've got Fe2, we've got both of the Fe2 pluses. Okay, we need Al3 plus. Where is that? Here we go. And there's Al3 plus. Okay. Now, to be quite honest with you, all you really have to do is look at the table. So we said that as you, the more positive the reduction potential, right, the stronger the reducing agent. These are the reducing agents, okay? And so as I move down this table, okay, I get an increase in strength of reducing agents, okay? And as I move up this table on the left side, I get an increase in strength of oxidizing agents, right? Okay, so now, copper cannot reduce this one. It's on the wrong side. It has to be something that's to the left, okay, of the arrow. So that one is automatically excluded. And you have to remember, if we keep a and it says spontaneously reduces, okay, that's important, because what do we have to have for a spontaneous reaction to occur? We have to have a positive cell potential. And that means everything that is below copper, it's not going to spontaneously reduce, because if we take this number minus the other number, we're not going to get a we're going to get a negative number. We're not going to get a positive cell potential. So really the only thing that copper can spontaneously reduce is anything that is on the left side of solid copper and is above copper. So everything that's up here it can spontaneously reduce. And the only thing in this column that was asked about was silver, right? So the answer here is silver plus. Okay. Now, if you don't like that approach, and you want to say, okay, I've got, right, copper, right, because we always put the more negative, right, because it's reducing, so we need it over here. So this is, it's the reducing agent, but that means that it was oxidized, right? The reducing agents are the ones that are oxidized. And so that means it's more negative. So this is the anode side, right? And this is where oxidation occurs. We always want to put the more negative to the left. And then we do our little number line, right? This is 0.34, okay? And then where is silver? Silver's above that. And what do we have? We have Ag solid and Ag plus, right? And what's our number for this guy? 0.77, 0.77, okay? And so this is our cathode, okay? It's more positive. We have reduction going on, okay? All right. So we know that when we write the reaction, remember, we need to put, we're always going to go, we go in alphabetical order, right? Anode to cathode. Okay, so here we go. And our anode is what? Let me see. Remember, this is where oxidation, and then cathode is reduction. That's positive, and this is negative. So I just, quick little reminder about that. Okay, now, if I take the half reaction of this copper, so I'm going to have copper that goes, and I'm taking it this way, right? Copper to, because it was oxidized, to copper 2 plus, okay, plus 2 electrons, all right? And that one is 0.34 volts. And then if I have, what's the other one? This is my anode. And so then if I do silver plus from this table, right, it's Ag plus, so this one is where reduction occurs, so we could keep it like it is. Zero, and then this is plus an electron to form silver solid, right? Okay, what's the first thing I have to do with these? We have to equalize, sorry, we didn't realize you couldn't see it. We have to equalize the electrons. Okay, and so this has 2 electrons, this has 1, so we're going to multiply it by 2, right? And it's going to give us copper plus 2 Ag, because these will cancel now, right? 2 Ag plus. All right, and then so I've covered those. So now I have what? Copper 2 plus solid copper. Okay, and then of course you want to check your charges, right? We're going to make sure you have the same amount of charges on each side. We've got 2 and 2, and we do our elements that in all of this should balance. I'm sorry, this is 2. I should have a 2. And so that was the thing, when you go to balance your elements, that I caught that, right? Because I should have multiplied that through, and I did in my head, but I didn't write it down. And this is a spontaneous reaction, okay? And so if I do my cell potential, right, and I take, 77.77 minus 0.34, I'm going to get a positive number. Let's see here. Right, so that gives me 0.43 volts. Okay, so all that checks. So it does reduce, right? But then, sorry about that. If I do, okay, what's the next one? We had iron 2 plus, right? So here's iron. Here's our iron 2 plus. Now this one is going to be which one? This one's going to be our anode, and this one's going to be our cathode, because it's a negative number, right? And the more negative goes to the anode, right? So what do we have going on here? We've got iron. Do our little horizontal line. We've got iron to Fe2 plus, and then we got copper to copper 2 plus, right? So, what's my potential here? Negative 0.45. And then I've got negative 0.34, right? And so if I look at here, I've got my anode, my cathode. So I've got iron to iron 2 plus 2 electrons, right? Because this is where the oxidation is going to occur. Right, and then here on my cathode, if I look at, and that's what we saw here. We just wrote it back the other way, right? Because we had oxidation. And here is my cathode. So what do I have? I've got Cu. I can keep this the same, Cu2 plus 2 electrons to go to copper solid. Right. You want to equalize your electrons, which just so happens they already are. And then when I look at this, right, what do I have? I've got Fe plus Cu2 plus to give me Fe2 plus copper. Now, what happened here? Right? What's happening with this? We have a decrease in electrons. And if we're losing electrons, what? We have oxidation going on, right? And if I have oxidation going on, right, then this is my reducing agent, is the iron, not the copper. And the copper's going from a 2 plus to a 0, right? So that's going to give me a reduction. So that means copper is my oxidizing agent. So here we're showing, all I'm doing is showing you what the table is already telling you, okay? All right. So let's do the last one, okay? What do we have now? We have this Al3 plus, right? So I've got Al to Al3 plus, right? And what's its value? I'm going to do my line. It's at negative 1.66, and then I've got my copper 2 plus. We know that one's 0.34, right? And so when we work this out, let's see, we've got, we know our anode is the aluminum. We know our cathode is going to be the copper because it's got the more positive charge. The more negative goes to the anode. Right, so when I look at aluminum, what do I have? I've got aluminum 3 plus to aluminum solid, so I need to write that. That's my oxidizing one. And remember, it's below, so we expect this to be the anode side. So I've got aluminum solid to form Al3 plus 3 electrons, right? And then I've got my, I can keep this because it's my cathode, so it's in the reduced form already, so it's Cu2 plus 2 electrons to form solid copper. Okay, so I need to equalize my electrons, right? So the least common multiple of these are 6. That's 2, multiply that one by 3, right? So that's going to give me what? 2. Let's see, and we'll cancel. That's 2 aluminums, right? Plus what? 3 copper 2 plus, right? And that's going to give me 2 Al3 plus 3 solid coppers, right? Okay, so when I look at this, what do I have? If I go from solid aluminum to, so here I'm going from 0 to a 3 plus, so that's a decrease in electrons. And what happens when I lose electrons? I have oxidation going on. Okay, then I go from copper 2 plus to solid copper, so here I've got plus 2 to 0, so I've got a increase in electrons, right? So I have reduction. So what does that mean? That means that copper is oxidizing aluminum. Oh, sorry, copper is oxidizing aluminum, and that's what our table tells us, right? Copper cannot reduce anything below it, and the only thing it can reduce is everything above it and to the left of the arrow. Okay, so see, you didn't even have to do all this table stuff. You could just, I mean, all the horizontal line stuff. You could just use the table, and that, I know it took a long time, but I was trying to prove a point. All right, so let's go on to the next one. We have which of the following is the best oxidizing agent under standard conditions? Well, let's see. What do we have going on here? So I'm going to use a different colored pen on this one. So we've got, which of the following is the best oxidizing agent under standard conditions at 25 degrees C? Okay, so when you look at your table and you see this E0, that means we're under standard conditions. So we can use this table, right? All right, and so it wants to know about the best oxidizing agent. Okay, and where are my oxidizing agents? They're to the left of the arrow, right? So let's look. What do I have? I have cadmium, and let's see where that guy's at. Okay, it wanted cadmium solid though, right? Okay, so here we go. This is why I say use different colored pens so you can keep up with what's going on. And then we have copper 2 plus. Okay, but we've got the aqueous, we don't want the solid, so we've got this guy. Okay, and then we've got magnesium 2 plus, aqueous, and we've got Cl minus. Okay, Cl minus is going to be up here. Okay, and then I have I2 solid. Okay, so that one's right there. Okay. Now, I want to know which of the following is the best oxidizing agent under standard conditions. Okay, well, here's the thing. We already looked at our table, and we know that as the cell potentials increase, what happens? The stronger the reducing agent as I move down this way. And so that means that the stronger the oxidizing agent is going this way. So, but it has to be what's to the left of the arrow. This guy, he's out, right? Because he's a reducing agent. We're asked about the best oxidizing agent, okay? So the best reducing agent, I'm sorry, best oxidizing agent in this case, and it's not going to be this guy, because which direction are we going? We're going up, right? And what's the cell potential on him? He's negative 2.37, so he's out. Right? It's I2. Okay, we just look at the table. It's I2. Now the next question asks just the opposite with the same answers. Which of the following is the best reducing agent? Okay, which of the following is the best reducing agent? Okay, so we said, like, okay, so as we move down this table, this guy, he's getting lower and lower and lower as an oxidizing agent, right? So he's not the best. this one is the best because which way is the strength? So you could imagine if I took this half of the table and just put it underneath here, right? And then you could see a better picture. This one was the lowest in oxidizing strength, and this one was the highest. That was my I2. Now we want to know which of the following is the best in reducing agent under standard conditions. Well, we know our reducing agents are to the right of the arrow, right? And as we move down the table, it's better. So which one is it? It's cadmium, right? It's this guy. This right here is what we call a distractor answer, right? Because you look down and go, oh, well, this one's the lowest, but it's on the left side. That means it's an oxidizing agent. It is not a reducing agent, and it wanted to know about the best reducing agent, okay? So make sure that you pay attention to that. Remember, the increase in strength in reducing agents are going to be to the right of the arrow. Increase in strength of the oxidizing agents are going to be to the left of the arrow. Okay, so now we've got a voltaic cell. It's constructed using a copper solid and a copper 2+ and a half cell of iron solid and iron 2+. Both half cells are at standard conditions. Okay, so that's good. We can use our table. The two solutions are connected to it with a salt bridge, and the copper electrode is connected to the iron electrode with a wire. Which statement is correct? Okay, so sometimes in these cases what we may want to do, that you can draw like your horizontal line, okay, or what you can do is you can do your you can draw like a picture of this, right? Okay, and so if either way, you know, you could draw a your cells here to see which one is your reducing agent and which one's your oxidizing. So where does the anode go? It always goes over here, right? So this should be my anode, and this should be my cathode. Think about that alphabetical order, right? Anode, cathode, right? And this is negative, and this is positive. And how do we know that? Because if we take an electrolytic cell and we take a voltaic / or galvanic, either one, keep it in alphabetical order. We do AC, right? We keep the plus on the diagonal of the matrix. This is minus. So here we know that the anode is negative, cathode is positive. You don't have to memorize this. If you think about it logically like this, you can figure that part out. Okay. Now we have copper 2+ copper solid. So here's this guy. It's when we do our little line. Okay, and then we have iron solid and iron 2+. So where are you? Right here. Okay, so this one is negative 0.045. We know this is our anode. Look how negative that number is, right? The more positive potential is going to go to the right. So the more negative to the left. Okay, and this is our anode. This is where oxidation occurs, and this is a negative sign, right? And what do we have here? We have, this is iron to iron 2+, and what was our negative 0.45, okay? And then we have, which one is it? Copper and copper 2+. Okay, and our value here is 0.34, okay? And how did the electrons flow, right? They're going this direction, right? Towards the cathode, right? So if we said we had iron here, right? And then here we have our copper, right? So this is copper, this is iron, and we've got our system going here. And how do these electrons flow? They're going to go this way, right? Okay, so it says electrons will not move through the wire because this is not a spontaneous reaction. It is a spontaneous reaction, okay? So we know that one is out. Electrons move through the wires towards the iron electrode, which is an anode. So it says electrons move through the wire towards the iron. It's not, no, they don't move towards the iron, they move away, right? They're going to move towards the cathode because they're building up and they're repelling one another, the electrons here, and that's what's pushing them out to move towards the cathode, which the cathode is copper, right? So that's out. Electrons move through the wires towards the iron electrode, which is cathode. Okay, so they move through the wires toward the iron electrode, which is cathode, but it's not, right? It's an anode, so that's out, right? Because it's anode. Okay. Electrons move through the wire towards the wire copper, which is, electrons move through the wire towards the copper electrode, which is the anode. The copper electrode is not the anode, it's the cathode. Okay, so that one's out. So what does that leave us? It says that electrons move through the wire towards the copper electrode, which is the cathode. And we can see the same thing here, too. This is two different ways to express the same thing. So this is our answer, okay? This guy, E is our answer. Okay, these say the same thing. You can draw the little pictogram or you can do your horizontal line. It doesn't matter, right? But you gotta think these through or you're gonna miss it, okay? All right. So a half cell consisting of a solution of nickel and 1 molar nickel and a nickel electrode is connected to a half cell consisting of a solution of 1 molar of iron and electrode from a voltaic cell, what occurs at the positive. Okay, well, let's look. So first thing we're going to do, we're going to draw our little line here and see who goes where. So what do we have? We've got nickel and nickel solid, nickel 2 plus, iron and iron solid. Okay, so we know we've got this guy. I think what we'll do is we'll just highlight this one this time. So we've got this one. See, this is why you got to bring all these different colors. So we've got iron, right, and then we've got nickel. Okay, so we've got this guy. Now, when I'm looking at my table, what did we say when we're looking at the table? Right, we want to go this way, that way, right? What goes this way? What goes forward? Cathode, anode, and cathode's always on top, right? So we want this like this, right? So this is my cathode, this is my anode, and it's going that way, okay? And they're going opposite directions. So when I look at that, what does that tell me? It tells me that nickel, it's on top, so it has a more positive number, so it's negative 0.26. This is my nickel to nickel 2 plus. Okay, and what's this guy? It's negative 0.45. The more negative always goes to the left, to my anode, where oxidation occurs. Remember, keep the vowels together. Anode, oxidation, left, more negative. Okay, and so what's happening here? This is solid iron going to Fe2 plus, right? Okay, so here's what we got, and it says, and what occurs to the positive electrode? Okay, so remember, you never have to memorize this. About the positive. I mean, you should know this is the more positive side. This is a cathode, right? And the cathode is the more positive side. But what did we do? We put anode, cathode. Keep it in alphabetical order, right? That's all you got to do is keep it in alphabetical order. And then we have what? We have an electrolytic cell, and then we have our voltaic slash galvanic or galvanic slash voltaic, whatever. They're the same, but they both, G and V both come after E, right? And we keep our positive on the horizontal of the matrix, and then there's our negative. So for this guy, for a voltaic or galvanic cell, okay, we have, and that's what we've got is a voltaic. We were told we have a positive side at the cathode. So at the cathode, what is going on? Nickel 2 is reduced at the positive electrode. Yes, this is true. We see that. Here we say nickel solid is oxidized at the positive. Nope, oxidation does not occur here. Okay, this is reduction. Iron 2 plus is reduced at the positive end. No, it's not. Iron is on the anode, right, on the negative side. Iron is oxidized at the positive. Iron's not doing anything at the positive end, okay, because it's an anode. Nickel is oxidized and iron is reduced to the positive end. Now this one you should just, if anybody chooses that, then you absolutely have no clue about what's going on. Okay, so A is the correct answer. All right. Okay. We can go back to this table now. Okay. All right. So maybe we can, maybe we can't. I don't know. All right, so what is the cell potential of the following under standard conditions at 25 degrees C? Okay, so we're at 25 degrees C. We've got some shorthand notation going on, and just as a reminder, I'm going to write out what that is, right? We always go in alphabetical order. So what this is we've got our anode. This is our electrode, right? The solid, and then this is the solution, right? This is the anode electrolyte. Okay, we put this here. This is a phase boundary, the single lines. This is our salt bridge, right? The double lines. And then we do cathode electrolyte. And that's going to leave us with our cathode electrode, okay? And in which way did the electrons flow, right? They flow this way towards they flow like this towards the cathode. All right, that's just a reminder of what's going on. Okay, so what does this tell me? If I follow this, this is my anode electrode, right? And this is my anode electrolyte. I'm just going to put an AE. This is my cathode electrolyte, and this is my cathode, right? And so this is the positive end, this is the negative end, okay? And so what's happening here? Oxidation is occurring here, and reduction is occurring here, right? We know this. And so, and we know that we need to do our horizontal line, right, to figure out how we're going to set this up for the cell potential. So we need to find aluminum on the table. So this is a different table. It's the one we started off with. All right, so we have aluminum here. All right, so we got aluminum 3+, but what's going on? We've got the oxidation, right? But we keep the same value in the sign. So we've got negative 1.66, and here's aluminum going to Al3+. Okay, and then that means that we have zinc and zinc 2+. So let's find, what was my aluminum? So I'm just going to circle this. And then, here we go, zinc and zinc 2+. And then what did we have? We had here negative 0.76 volts, right? Okay, and so, oh, I'm sorry. And now we need to calculate the cell potential. I'm trying to fit all this in, and I can't. Let me get you guys. There we go. Okay, so now what do? I'm going to do the cell potential now. So where we do, the cell potential is equal to the cathode minus the anode, right? So we're going to do the cell potential is equal to negative 0.76 minus, and then we'll put a parenthesis here, minus 1.66 volts, all right? And that is equal to a positive 0.90 volts, okay? It's real important that you do your math correctly, okay? Some of these values, such as this one here, will equal if you do this wrong, okay? So you want to make sure you set these are not arbitrarily wrong answers. These are set up so if you do your math wrong, you'll think you got the right answer, but you didn't. So just follow the formula, okay? All right, so a zinc-silver voltaic cell could be constructed by attaching zinc to a half cell and silver to a half cell. What is the cell potential at 25 degrees for this voltaic cell given the following concentrations? Oh, so what's happening here? We're no longer at standard conditions. What conditions are we at? These are non-standard. Non-standard conditions, okay? And so when we have non-standard conditions, we're going to have to use the Nernst equation, right? So let's set this up. What do we have? We've got, we need to look at the potentials again. We've got this zinc, and this time, let's see, we'll do green. Well, no, you don't highlight in green because I've already got the zinc and the zinc 2+ on the table. See, this way you got to have all these bring different colors and highlighters to the exam. I'm serious about that. It'll help you. So we've got zinc 2+, and then what is the other one? Oh, we had silver 2+, right? So silver plus, Jesus, can't we said 2+? There's no such thing. Okay, so this is what we're working with. All right, are these guys here? Okay, and so which one is my cathode side, which one is going to be my anode side. This one's further down the table, right? So we're going to keep this as a reduction. This is the more positive side. It's got a more positive value. So if I do my little number line, right, my horizontal line, then I know on here I have Ag to Ag plus, and here's zinc and zinc 2 plus, right? So it's, see, and if you notice before in the oh, I'm way down here, I'm sorry. In this problem, zinc was a cathode. Now zinc is an anode. See, there's no guarantee. It just depends on what they're being compared to. All right, so we've got non-standard conditions, right? Got our number line set up. We know what's happening here. This is our anode, right? And oxidation. Keep those vowels together, AO, and keep the constants together. We've got a cathode, and what happens at the cathode? Reduction, CR, right? Reduction. Okay, and so, oh, let me write these values down. All right, so for the zinc, what did we have? We had negative 0.76. Negative 0.76. And then for the silver, we had 0.80. Okay, so if we want to know our cell potential, because we're going to have to plug that into the Nernst equation, right? So E naught cell is equal to 0.80 minus negative 0.76, right? And that's going to give me my cell potential. And then what are we going to do? We're going to go ahead. We have to set up our balanced equation because we need the number of moles of electrons to equalize this, if that's what we need. Yeah, if they're not already set up, we got to do that so we can have that to plug into the Nernst equation as well. I think this should be 1.56 volts. Okay, if you guys get something different, just message me. But that should be okay. Now this is the cell potential, the standard cell potential. Okay. And remember, for the Nernst equation, what do we need? Well, first of all, we need to do our balanced equation. So what do we have? We've got our anode. We've got our cathode. And what's on the anode end? Anode end is zinc, right? And so if we look at our half reaction up here for zinc, all right, we're oxidized, right? So we need to do zinc solid to form zinc 2 plus. So we have zinc to form zinc 2 plus 2 electrons, right? And then what was the other one? We had our cathode side was silver, so we want to keep this as a reduction, so we're going to do silver plus 1 plus an electron to solid silver, right? So we're going to do silver plus plus an electron to form solid silver. Okay, so when we do this, we're going to have to equalize the electrons here, because I've got 2 here and 1 here. Okay, and so what is that going to leave me? I've got I'm going to leave this guy, so I've got zinc, right, plus I have to multiply this one by 2 so I can get rid of this. So I've got 2 silver plus, right, to form, so I've done that one, zinc plus, zinc 2 plus, sorry, and then 2 solid silvers, okay? And then we just want to check our charges. I've got a total of 2 plus charges here, 2 plus charges here, and then we want to check our atoms. I've got 1 zinc, 2 silvers, 2 silvers. We're good to go, okay? Right, so that guy's balanced. So now what do I have to do? Now I can get into my Nernst equation. And why did I have to do this? Because I needed to know what N is, right? I needed to know N. And N is the number of electrons needed to equalize this. What did we have? We had 2, right? So whatever these are, once they're equalized, that's our number of moles of electrons. And so now we have the cell potential minus, I'm sorry, that's not how this works. We have the cell, yes, we have the cell potential minus the equal to the standard cell potential right, minus 0.0592 over N times the base 10 log of Q, okay? And so we got to look at some things then. What is my concentration of this, of silver plus? What's my concentration of silver plus? It's 0.0020 molar. So, okay, so it's 0.00200 molar. Okay, and then of my zinc 2 plus, it's 0.0200. Now remember, what is Q? It's products over reactants, right? Okay, so what is this guy going to be equal to? Do him another color. So we have E is equal to, we already figured our cell potential, right? It's going to be 1.56 volts, right, minus 0.0592, and then what is my number of moles? It's 2. That's the electrons that I've got, right? Because you have to have the same. If I gain 2 electrons, I got to lose 2 electrons, and they have to be the same in the cathode and the anode. So my number of moles is 2 in this case. Okay, and then it's just, we have log, and now we need to do products over reactants. Okay, so this is a product. I've only got 1 mole of this, so I've got 0.0200 on top. And what's on bottom? How many of these do I have? Well, I've got 2 moles of this. I have a coefficient of 2, right? So I have 0.00200 raised to the power of 2. Okay, and when we plug all that into our calculator, okay, we're going to get this 1.45 volts, and that's our answer. All right. So, in order to solve a problem like this, one, you have to look at this and realize it's not under standard conditions. And if it's not under standard conditions, then what does that mean? We're going to use the Nernst equation, right? Which is the cell potential is equal to the standard cell potential minus 0.0592 over N. N is the number of electrons that we're canceling out, number of moles of electrons times the base 10 log of Q, which Q is our reaction quotient, which is products over reactants, okay? And you have to remember to raise it to its proper coefficients. All right. And so that's why you have to balance the half-cell reactions, because you need the number of moles. You have to do this because you have to determine the standard cell potential, okay? Once you have these things done, then you can plug it into the Nernst equation. So there's like basically 3 steps, okay? All right. Now let's move on to this one. We have a copper cobalt galvanic cell can be constructed by attaching a standard copper half cell, standard cobalt half cell. And the notation for this galvanic cell is here. So what does that mean? That we have an anode. This is our anode electrode, right? This is our anode electrolyte. There's our salt bridge. Remember, this is a phase boundary right here. The double lines is a salt bridge. This is our cathode electrolyte, and this is our cathode electrode, right? What happens at the cathode? Go ahead, and I should do this. Sorry. What happens at the cathode? It's reduction, right? Right. And then this is our positive end. What happens here? Oxidation. It's our negative end, right? Okay. So we've got this. I just want to make sure that you know what you're reading here, okay? And so it says the galvanic cell has a standard cell potential at 25 degrees C of 62 volts. So that means that the standard cell potential, when you work this problem out, is equal to 0.62 volts. We were given this information, okay? What is the standard reduction potential for cobalt at 25 degrees C? Okay, well, we can figure that out, right? So, what are we going to do? We're going to do our number line, okay? And then we're going to, we don't know, well, we do know because it was given to us. It says that copper, here's our cathode. So we got Cu, 2 plus, and it tells us that cobalt is our anode. sorry, that's a C little o, 2 plus. If I do C big O, that's carbon monoxide. Okay, so let's get this table where I can cover some stuff up. Okay, now, what do I have here? Okay, so let's see if I can even find cobalt on here. Maybe I can't. If I could find cobalt, it'd be easy enough, right? It's not on here. Now, this is just a small reduction table. There's reduction tables that are like whole books for people that do EPM. But I do know that I do have copper 2 plus, right? I know what that guy is. And so, what can I do? I can go ahead and plug that in. That's 0.34 volts, right? And so and then what do I have here? I know that my cell potential, that the distance from here to here, right, is 0.62 volts. But I don't know what this is. This is what I'm looking for, okay? And so what am I going to do? It says that what is the standard reduction potential, okay? Well, I know for cobalt. So I know that the overall cell production reduction potential is here we have. I'm just gonna write out what I'm looking for. Right, I want the standard cell reduction potential for cobalt and cobalt 2 plus. And so what am I going to do? I'm going to subtract these. Right, I've got 0.34 minus 0.62. And that's going to give me negative 0.28 volts. Now, if you're not sure if you did that right or not, okay, all you have to do is go back in and say, okay, the standard cell potential for this is, we said 0.34 minus negative 0.28, okay, and you plug that in and see if you get negative 62 volts, right? So if we do 0.34 minus negative 0.28, we get 0.62 volts. So it checks, right? We did our math correct. Okay, and so we have negative 0.28, and it's okay that this is negative because this is not the overall cell potential. Right, this is just the potential for the half cell, not the standard cell potential. Okay, all right. So now we have chromium. Chromium can number 14. Chromium can be electroplated onto a steel surface of an automobile bumper. This can be done by electrolysis. Oh, look at that. We're not talking about a spontaneous reaction anymore. Electrolysis of an aqueous solution containing sulfuric acid and chromic acid. What current is required to deposit chromium at a rate of 1.25 grams per minute? Okay, so we've got some things going on that we need to pull out of what this problem is saying. All right, so I'm not going to try to balance this whole reaction. I'm going to work with what was given. Right, I've got this H2CrO4. This is my chromic acid. Right, it says done by electrolysis of an aqueous solution containing sulfuric acid and chromic acid. Okay, and it wants to know what is required to deposit chromium at a rate of this. Right, so I'm going to take the chromic acid plus I need to know what the oxidation state of this. So it's going to be however many. I got to find the number of electrons. Right, I need to find the oxidation state of chromium, and I'm going to say that's going to form to get to my chromium solid. Okay, so let's look at this. If this is minus 2 and this is plus 1, then what I actually have is minus 8 plus 2 equal to 0. So that's going to give me a negative 6, right? What number do I need to make this whole thing overall neutral? I need chromium to be a positive 6, right? So this is plus 6 electrons. Okay, so you have to know the oxidation state of chromium to do this. Okay, and what are we going to do? We're going to have to use some stoichiometry here. Okay, this is why we have to know the number of moles of electrons, because we're going to have to use the Faraday, right? And another thing we need to keep in mind is, well, we'll get to that in a minute. So the first step that we're going to do is we're going to write down I is equal to Q over T. Okay? So we've got our current charge in our time, right? And so what were we given with this? We were given let's see, chromium was electrostatic. This is required to deposit chromium at a rate of 1.25 grams per minute. Okay. So I know that I'm going to need to get this in units of seconds, okay? And so I'm going to need this in charge per seconds, right? All right, so sorry, I had to stop for a second. I had someone at my door. Man, I'll be so glad when we can go back face to face and not having to do these videos where it just records me while I'm talking to you and you guys can ask questions. But anyway, all right. So again, I didn't do a balanced equation because what I'm looking at here is I needed to know this oxidation state here, right? Because I've got 6 chromium. An oxidation of +6 to 0. Right, so I know that what's happening here is for every 6 moles of electrons that I'm gaining here, from this, I'm going to do what? I'm going to plate out 1 mole of chromium. Okay, so I needed to have that ratio because we're going to have to use this, right? So there's 2 key steps here, and the first one is that we want to use the definition of current, right? So this is current, where we say I is equal to Q over T. We have to also keep everything in SI units. This says it's 1.25 grams per minute. Well, I know that I'm going to have to get this in seconds, right? So let's just assume that this is 1 minute, so that makes this time 60 seconds, okay? But we don't know what the charge is. We need to know this guy, right? We don't know. We need charge. So we're going to have to use the Faraday so that we can determine the number of coulombs, right? So we're going to have to do some stoichiometry. So we want to know the number of coulombs. We're going to set that equal to our given measured quantity, which is 1.25 grams per minute. Okay? And so, I'm just going to keep this as grams because we're solving for charge and we've already got our time here. All right, so it's grams of chromium times, and what do we do when we want to go from moles to grams, or grams to moles? Well, you need to use the molar mass, right? So for every 1 mole of chromium, I have what? 52.00 grams of chromium. Of course, the 52 came from the periodic table. Okay, now we always do what? This is stoichiometry, so we always need to think what? Mole to mole ratio. But the mole to mole ratio of what? Well, it's these electrons, right? I need to know. So I know that for every 1 mole of chromium that I played out, I have 6 moles of electrons that I have to that I'm gaining here to plate out this 1 mole of solid chromium. Okay, but I want to know about the charge. Okay, so I don't want to know about the moles of electrons. So how do I go from moles of electrons to a coulomb? I have to use the Faraday ratio, right? So I'll say for every 1 mole of electrons, I have what? 96,485 coulombs, right? Okay, and then I cancel my units. I want to know the number of coulombs. I'm left with coulombs, and when I multiply all this out, I'm going to get 13,916 coulombs. Okay, that's not my answer. Where does this guy go? Right? We have to put him here. Okay, and so that is going to equal to 13,916 coulombs over 60 seconds. Okay, and that's going to equal, now it just so happens that that coulombs per second is equal to 1 ampere. Okay, that's why these units are in amperes. All right, and so when I multiply this out, I'm going to get, or divide this all out, I'm going to get 232 amperes. Okay, and then this one is my answer. Okay, so when you approach a problem like this, the first thing that you're going to want to do, you got to keep up with your key things, right? You need to use the definition of current because you were asked what current is required to do this, right? And then you want to think about finding your charge. If you're not given charge, you're going to have to use the Faraday, so you're going to have to use stoichiometry. If you use stoichiometry, you're going to have a mole-to-mole ratio. That's what stoichiometry is, right, or the mole-to-mole ratios. So then that's when you look, okay, this is the acid that, chromic acid is the one that we're going to use because that's the one that has chromium in it, and that's what's needed to plate this 1 mole of chromium, right? And what we're looking for is the change in oxidation state because we need to know the number of moles, and we know this is why it's so important for you to understand how to determine the oxidation state of each element within a molecule, okay, or within a compound. And so we found that, and we said, okay, so we've got, for this chromic acid here, we're gaining 6 electrons to plate, 6 moles of electrons to plate out 1 mole of chromium, right? And we need all of this to plug in here, okay? So now let's look at the last one. All right, so gold plated from a solution of chromic acid, I'm sorry, not chromic acid, this is called caloric acid. It's a mouthful. It depends on, it deposits on the cathode. Calculate the time, okay, so now we want to know time, in minutes it takes to deposit 0.5 grams of gold under a constant current of 0.10 amperes. The molar mass of gold is 197. Okay, so again, we're not going to write down the entire equation for this, okay? Put this down a little. There we go. I can move this down. Okay. And so now, what we're going to do, just like we did before, so we need this guy, so we do HAUCl4, okay? And then we need to determine the electrons, okay? This is plus whatever number of electrons to do what? To get this, to get a mole of gold plated, okay? All right, so we know that Cl is a -1. This guy is a +1. We need to know what the oxidation state of the gold is, right? So technically this is -4, okay? And there's only 1 hydrogen, so that's +1. And so what is that? That makes it a -3. What does that make gold? It has to be a +3 to offset this, right? And so that means this is +3 electrons, okay? So make sure you can determine oxidation states. You really should be able to do that in your head. I just do it on the notes, so if you still don't have it, you can kind of walk yourself through. All right, so each gold gains 3 electrons, okay? And you want to make sure that the sum of the oxidation states equals the overall charge, which here the overall charge is neutral, okay? All right. And so we want to look at our key steps. The first one is to define, we're going to use our definition of current because that has time in it, right? So we have current is equal to Q over T, which is charge over time. So we can rearrange that to say that time is equal to Q over I, right, which is charge over current. Now we know that we were given how many amperes. This is equal to current, right? So what is that? That's coulombs per second. So that's the same thing as amperes. So we were given, we don't know what the charge is, but we do know the amperes at 0.10 amps. So we need to find the number of coulombs again. So that is step 2. And how do we do that? We use stoichiometry with the Faraday. So we say the number of coulombs is set equal to what? What's my given measured quantity? It's 0.50 grams of gold. Okay? And then we're going to use the molar mass of gold to go from grams to moles. So we know that for every 1 mole of gold, we've got how many grams? 197.0 grams of gold, right? We're going to cancel these units. What's the next step we always do in these mole-to-mole ratio these stoichiometry problems? I just told you mole-to-mole ratio, right? But mole-to-mole ratio of what? I need to know the number of electrons gained to plate out 1 mole of 1 mole of gold, right? And so I'll say for every 3 moles of electrons of gold, I get 1 mole of gold, right? Okay. Okay, so we cancel that out. But I don't want to know the number of moles that I have. I want to know about the coulombs. So I'm going to use the Faraday. So for every 1 mole of electrons, I have 96,485 coulombs, right? Okay, and what does that leave me? I wanted to know coulombs, and then I'm left with that. All my units canceled out, and that gives me 734.8 coulombs. Okay, so I'm going to write that here. It goes here, 734.8 coulombs. Now, we're not done, okay? We're not done. We have to, because what did it say? It wants this answer in minutes, okay? So, first of all, I'm going to just calculate this out, and it's going to give me, let me do it in a different color. It's going to give me 7,348 seconds, but I don't want seconds, right? I want minutes. So I know for every 1 minute, I've got, 60 seconds, okay? And so these units are going to cancel, and when I plug all this in, I'm going to get 122 minutes, right? And so when I look here, I don't have 122 minutes, but I have 120, right? And so that's just significant figures, right? We can round this down. So I've got 120 minutes, okay? All right. Now, let me see. Is that the last one? I think so. Yeah, I think we're going to start in chapter 12 next. Yep. All right, guys, that concludes the practice problems for chapter 11. Please practice these, okay? Make sure that you understand how to pull this information out of the problems. Work your end-of-chapter problems, all right? I promise you it'll reward you if you do that, okay? All right, that's all I've got for you, and I hope this helps. And if you have any questions, just send me a quick, I don't know, Teams message or email, and I'll get back to you.